Welcome to The Explainer. Today we're diving into a high-stakes medical mystery ripped straight from the front lines of modern medicine. We're going to unpack a brilliant 2026 multi-center study out of Taiwan that tackles a seriously daunting question. What do we actually do when our strongest medicines just stop working? We're going to look at exactly how a remarkably simple dosing change of a very familiar drug is literally defeating an incredibly deadly superbug. Okay, let's take a quick look at our roadmap. We'll be covering the superbug threat, the dosing dilemma, how high dose saves lives, decoding the breakpoints, overcoming antibiotic resistance, and finally, a new treatment standard. Let's jump right into Section 1, the superbug threat. Now, before we can really appreciate the cure, we've got to understand the enemy we're facing in our hospitals. Enter CRAB. That stands for carbapenem-resistant Acinetobacter baumannii. It's a formidable superbug that actively resists our strongest, most reliable treatments. In fact, it's so dangerous that the World Health Organization officially categorized it as a critical priority pathogen globally. I mean, just imagine a loved one in the ICU on a ventilator. If they contract healthcare-associated pneumonia caused by CRAB, the mortality rates are just incredibly high. So it's a massive priority target for infectious disease specialists all around the world. Which brings us to Section 2, the dosing dilemma. So how do we fight an enemy that completely ignores our best weapons? Well, sometimes we have to turn to older drugs, specifically a drug called Minocycline. But that introduced a huge dilemma for the medical community. They knew Minocycline could be a potential weapon against SCRAB, but they were totally torn on exactly how much to use. We essentially had two competing regimens. On one side, high-dose therapy at 200 milligrams intravenously every 12 hours. And on the other side, standard dose therapy at 100 milligrams every 12 hours, or maybe just 200 milligrams once a day. For years, doctors were stuck with sparse, conflicting data. Some older studies claimed the high dose worked best, while others actually warned it had lower cure rates and higher mortality. It was, honestly, a complete guessing game with real patient lives on the line. Moving to Section 3. High dose saves lives. That guessing game basically continued until this 2026 Taiwan study came along and just completely shifted the paradigm. Let's look at the dramatic findings from this multi-center retrospective study of 106 patients. The researchers looked at patients hospitalized with this severe pneumonia. In the standard dose group, the in-hospital mortality rate was 48.3%. Nearly half the patients didn't make it. But in the high-dose group, that mortality rate plummeted to 28.6%. By simply optimizing the dose of the exact same medication, doctors saw a massive reduction in deaths. Absolutely incredible. And the statistics backing this up are incredibly robust. The researchers didn't just look at the raw numbers, they adjusted the data for severe baseline differences. Because remember, many of these patients were incredibly sick to begin with. We're talking suffering from chronic kidney disease, solid tumors, or even undergoing chemotherapy. To put this into perspective, even after adjusting for all of those severe, life-threatening comorbidities, high-dose minocycline emerged as the only protective factor against in-hospital mortality. It boasted a highly significant adjusted odds ratio of 0.183. Basically, this means it actively protected patients from death when literally nothing else did. When tracking patient survival over 150 days, what's absolutely crucial to notice is how the outcomes for the two groups don't just separate early on. They stay apart. The gap in survival actually continues to widen over time. This proves that the higher dose doesn't just offer some quick, temporary fix. It provides a profound, long-term, life-saving impact. All right, Section 4, decoding the breakpoints. Here is where we really have to put on our detective hats to solve a lingering mystery about the lab results. Because as we know, in medicine, simply knowing a dose works isn't enough. We need to know exactly why our lab tests were failing to predict it in the first place. For a long time, doctors were noticing a really frightening trend. They take a sample of the bacteria, test it in the lab, and the lab would say, yep, the superbug is susceptible to minocycline, so the green light was given. But when doctors gave the standard dose treatment based on that specific lab data, the patients were still failing miserably and passing away. Why was that happening? Well, the answer lied in something called minimum inhibitory concentration, or MIC breakpoints. You can think of a breakpoint like a threshold on a lab test that essentially tells a doctor, yes, this drug will work, or no, this bug is resistant. The old standard, the CLSI 2024 breakpoint, said that if the concentration needed to stop the bacteria was 4 micrograms per milliliter or less, the bacteria was categorized as susceptible. But that threshold was simply way too high. It was giving doctors a total false sense of security.
The new standard proposed by the study is the PK/PD breakpoint, which is a much, much stricter threshold of 1 microgram per milliliter or less.
And the mortality numbers perfectly validate that new, stricter standard. Under the new PK/PD breakpoint of 1, if you had a bacteria that met this strict threshold and the patient got the high-dose treatment, the mortality rate was an astonishing 0%. Zero. But under the old CLSI 2024 breakpoint of 4, the mortality for high-dose patients remained exactly the same whether the bacteria tested below or above the threshold. The old breakpoint completely failed to differentiate survival risks. It was functionally useless for predicting clinical success with standard doses.
Section 5. Overcoming antibiotic resistance.
So how exactly is this high dose physically overpowering this stubborn bacteria on a molecular level? Let's geek out and dive into the biology. It really comes down to 4 incredible mechanisms. First, minocycline's effectiveness is driven by the concentration time curve, the AUC/MIC ratio. The high dose simply keeps enough drug in the system for long enough to kill the bug. Second, this superbug uses a defense mechanism called a TET-B efflux pump. It literally pumps the antibiotic right out of its own cell as fast as we put it in. By doubling the dose, the treatment just completely overwhelms these pumps. They literally can't spit the drug out fast enough. Third, this optimized high dose forces maximum medication penetration directly into the lung tissue, exactly where the severe pneumonia lives. And fourth, minocycline has known secondary anti-inflammatory and immunomodulatory benefits, cooling down the body's dangerous inflammatory response, which, as we know, often kills patients even after the bacteria is technically dead. Now, you know doctors rarely use just one drug against a superbug. They usually combine minocycline with other heavy hitters. So the researchers had to ask a really important question. Was it the high-dose minocycline saving lives, or was it the drug it was paired with? Well, when they looked at the combination therapies, pairing minocycline with cephalosporins, piperacillin tazobactam, carbapenems, or colistin, they found no significant statistical difference in outcomes across the board for the high-dose recipients. And this confirms our main suspect. It wasn't some magic combination of drugs that saved lives. The companion drug didn't drive survival at all. It was the sheer, optimized force of the high-dose minocycline itself, acting as the true hero in this fight. It's just wild to see the data prove it so clearly. Let's wrap things up with Section 6, a new treatment standard. Let's see how this data directly builds the future of medical guidelines worldwide. Because listen, this isn't just an interesting study that sits on a dusty shelf. It is actively changing how medicine is practiced today. The compelling evidence from this study heavily supported the critical 2025 CLSI guideline revision. The Clinical and Laboratory Standards Institute literally lowered the minocycline susceptibility breakpoint for Acinetobacter down to that strict 1 microgram per milliliter threshold. This forces hospitals worldwide to finally stop relying on flawed lab interpretations, completely rethink individualized therapy, and adopt the stricter, life-saving susceptibility breakpoint. This entire story is a massive victory for medicine and for patients everywhere. By simply optimizing the dose and adjusting how we read our lab results, we are successfully fighting back against a WHO critical priority superbug. But it leaves us with a vital question to ponder. As bacteria continue to evolve at absolute lightning speed, are the rest of our standard dosing guidelines adapting fast enough to ensure we're actually ready for the next bacterial evolution? It's something the global medical community absolutely must continue to aggressively investigate. Thanks for joining me on this explainer, and keep asking the big questions.